Hello again. Welcome to AP Statistics, Session 2, and Section 1.2 today. Hope you are, again, well, you might be still watching from 1.1 and continuing forward. If so, welcome back, and let's get it underway. We've got Section 1.2 here, and let's get it rolling. We're going to kind of throw this underway. All right. Before we talked about conditional distributions, marginal distributions, if you're still with us, I'm glad. I'm glad you're still with us. We've got a lot of definitions that we covered a couple of on section 1.1. And what we're going to do is we're just going to continue off that and continue forward on a lot of these specifics here. Today we're going to talk about distributions in terms of different types of quantitative data. Okay, so how do we display quantitative data? And that's really the question we're going to ask. The first thing we like to do, and when describing or when placing data within a distribution, we use a thing called a dot plot. If there was one specific idea that you would want to make sure you note, it would be dot plots in terms of setting them up with quantitative data. Again, quantitative data is, throw it out there. Yes, that's correct. It is the data that is measurable. It's quantitative. It's normally related with values, right? And we like to use dot plots in order to measure them. Now, normally it's traditionally kind of like a number line if you look at it below. And the one thing to remember within this is we must have a label on this. So if we were looking at the number of goals scored by the 2004 U.S. women's soccer team, because that's the only team that actually, that's the only soccer team that actually can make the World Cup, because they're so legit and the guys are awful. In 2004, we noticed that their games that were scored, or their goals scored per game, was represented as the following. So 3, 0, 2, 7, 8, okay? What we did on this is then created a number line which was represented below, where each of these dots correspond to one game. So if you looked at one of those dots, that one dot would be 3 goals scored within this one game, okay? 3 goals scored in the one game. And once I label or put this distribution out, we would call that a dot plot, okay? So you'll notice that as I go down here, like for instance, in 1, you have 1, 2, 3, 4, 5, 6, 7, 8. So that means in 2004, there were 8 times they scored 1 goal. Okay. Again, this would be a quantitative measurement. We label that by drawing the horizontal axis. We did that. Labeling it, scale the axis. So you want to make sure that it's kind of set up to where you have 0, 1, 2. So don't skip numbers. Make sure it's consistent there. And then mark a dot for every time that location occurred. So as you go through, like if I was to label this, you'd have 1, 2, 3, 4, 5, 6, 7, 8. 8, which is just what we found, 8 times where they scored 1 goal within that season. So 8 games, they scored 1 goal. All right, so when we use this, or when we talk about these distributions, from a quantitative standpoint, there will be a FRQ, which is a free response question that is at the end of, it's the second part of an AP statistics exam, where they will state at some point, they want you to describe the distribution, okay? And what we're trying to do is we're trying to identify and understand what is the data telling us. What is the data telling us, okay? So we want to make sure when we look at this data, we look for specific overall patterns and specific departures from that specific pattern. So we describe it using this keyword, okay? Please know this word, okay? If you need to get a tattoo of it, no, don't do that. But you need to know the word sucks. We describe a quantitative measurement, quantitative data, a distribution, or the setting up of this data by using SOCS, and it's labeled like this. We talk about the shape. We talk about shape. We talk about outliers. Is there any data? An example of an outlier would be something like if we had a dot that was way out away from all of the rest of the distribution, we call that an outlier. What is the center and what is the spread? Okay. So we have shape, outlier, center, and spread, and that's how we distribution that is quantitative. Okay. And so that's how we would describe it. Again, here's just another definition. Individual values that fall outside the overall pattern, that's called an outlier, okay? So as we look at something, we'll actually go back here. I want to look at this one. If we look at the bottom distribution, this dot plot, we can describe the center as the number that's approximately in the middle. So we'll talk more about what center is and how we would describe that and how we talk about it. But we would say center is approximately between 2 and 4, okay? Probably if we talked about it a little bit more, probably would be right at 3, okay? So center's where the middle is. The spread is the spreading out of data, okay? You can think about the spreading out of data. Sometimes distributions and dot plots are more or less spread out depending upon what we're focused on or looking at. Outliers, I don't see any real outliers. Maybe 8, maybe 8 could be an outlier there. And then as far as the shape is concerned, you'll notice that the shape kind of goes down that way. We're going to talk more about shape in terms of what we're expecting within that. Okay? But just so you have a heads up on that, that would be more or less what we're talking about when we say socks. Okay? Now let's take a look at this one. Brian and Jessica have decided to move and are considering 7 different cities. Each of the cities is represented as A, B, C, all the way to G. Help them pick a city by answering the questions below. Okay, I just covered that, I know, but just act like you didn't see it. All right, so question 1. What is the most important difference between A, B, and C? So the question that we have is, as we look at socks here, we are looking at A, B, and C. What is the most distinguishable difference between them? Well, first off, let's talk about the shape. The shape of this is something that looks, we call that approximately normal. Okay, we'll talk about that later on. But this is approximately normal and approximately normal. The shape of this does not look much different from one to the other. So we would say that the shape would stay the same. The second question we have is, are there any outliers? Well, as you look down on E, you'll notice that we actually have outliers here and here. But as we look at A, B, and C, there are no outliers that are away like this from the data. So we would say that outliers, there are no outliers there. The third thing we're going to look at is the center. Is the center different? Well, as we look at the center will be approximately about right in there for part A. For part B, which would be, if we look down, would be like at 0.9, right? For part B would be more towards 0.7. And for C would be more or less towards this 0.8 that's there. So as we look at that, you'll notice between A, B, and C, we have 0.9, 0.7, and 0.8, which is the major difference between the distributions of A, B, and C. So we would say that in this case, center, as far as right now is concerned, center is the big difference between our 3 distributions. Let's look at our last one, which is our spread. Again, this is the spreading out of data. An easy way to look at spread is we look at range, which is our high minus our low. But as we look at our high minus our low, that distance here and here, and the distance between here and here, and the distance between here and here, though they've shifted, the distance remains the same. So the spread actually would not change. And so we would say that center would be the major difference between question A. Okay. All right. So let's go to the second one.
Oh, okay.
Number 2, I'm not talking to myself. I've got Torrance and Mason. They'll probably be watching this, so you'll be watching yourself a little bit later. So it's a little stats action. So they're joining us today. Question 2, what is the most, that was funny because you thought I was actually talking to myself, which was pretty good. What is the most important difference between cities C and D? So as we look at this, I'll kind of rewind here. But as we look at C and D, we again look at shape, outliers, center, and spread. So as I look at C and D, let's take a look at it. So let's talk about, first of all, the shape. The shape of this is, again, approximately normal. It's kind of got one hump there. And if I were to follow the pattern here, kind of hits the top and then levels down. Even though that does look different, the shape would still remain the same because it's still got only one hump around right in the middle. So even though it's like, basically it's like pulled, the tails have been pulled, the shape, it will remain the same. Each of these do not have any outliers that are on the outside, like if I put one there, so it's not there, so outliers are good. The center for C is about right here, and D would be about right there. So it's approximately the same, give or take. So we'll say that that's the same. But the spread is the biggest difference, because as I look at this, the distance between the highest value to the lowest value on C is much lower than the highest value to the lowest value on D. So I would say that in this example, that the biggest difference on this would be the spread. Okay, that would be number 2. I want you right now to see if you can do numbers 3 and 4. Pause the video, do numbers 3 and 4, and then we'll come to it. So we'll hold off. And we're back. All right, so hopefully you paused it and you got it right. Let's look at 3. What are 2 important differences between D and E? Let's see here. Y'all know? What's the difference between D and E? I know you just hopped in here. All right, so let's look at it. D and E. So we have SOX, right? You have shape, outlier, center, and spread. So let's talk about the shape first. The shape here kind of comes here and then again has one hump. D does too, kind of one hump and then comes down. So I would say that that's approximately the same. Outliers, there's not really an outlier that's away on D. However, is there an outlier on E? Yeah, big time. So I would say that outliers is definitely something that's different from D to E. What about the center? Well, the center will be approximately here, and E would be approximately there. So they may be a little off, but relatively they're the same. And what about the spread? I would say that the spread would be pretty much the same, right? Because you've got here and here. That's the spread of that data, whereas the spread would be from here to here on that data. So again, approximately the same. So as we look at it, it said 2 things, but we kind of found one. I would say that outliers, definitely. And the one thing with spread, because these 2 things are outliers here, I would say that really these are thrown out. A lot of times we throw out our outliers. So really the spread, we would say the majority of the data is right here to here. That's why in that one, we would say that spread would also be there as well. And again, this is, if we use the range, obviously they would be the same, but we're going to talk later how spread is actually more than just maximum minus minimum. But for what we talked about, you probably said outliers, so you'd be right. Next thing, what is the most important difference between CF and G? So we're going to look at there. CF and G would be here, here, and here. Okay. Well, on this one, C would be there, F would be here, and G would be here. Out of SOX, which one would be the biggest difference? Shape. Say again? Shape. Shape? Exactly. Exactly right. Because what happened? Here's the center. Here's the center. Here's the center. Approximately the same. We would state that the biggest difference is the shape of the data. Because up here, this is approximately normal. Over on F, we call this, wherever the tail is, like wherever it's out, we say that it's skewed that way. So we say that it is skewed right. That makes this one skewed left, because wherever the tail is, right? And that's how we would write it there, okay? All right, so we've got that one. Okay, so let's examine the data real fast as we kind of keep going here, okay? Are y'all good with it? I'm just doing this podcast. Y'all good with that? I'll come to y'all in just a second. All right, so we see that this is the distribution of a table for Environmental Protection Agency. If I said to describe the shape, center, and spread of the distribution and to really talk about stocks, let's talk about what we would state there. The first thing that you want to make sure of is you want to make sure that you put context in. Okay? Context. Context is key. If you do not put context, you will get the entire thing wrong on those FRQs. So you must state what you're talking about. So if I was to write about the shape, center, spread of the distribution, I could state a bunch of different things in terms of describing it. But let's talk about and then the context we'll get to here. But let's talk about the shape. The shape of this kind of has a kind of a weird shape. So a lot of times when we describe it, we use LY words like approximately or yeah, approximately is kind of what we use slightly sometimes. But in this case, we would state that there's only like one hump here. So we would say that this is approximately normal. Okay, we'll talk more about that later because I know this vocab is new here. Outliers. Are there any outliers here? I would say maybe, right? Maybe at 14 and 18. So I would state maybe 14 and 18. We'll have a definitive way of finding that in a little bit. The center is approximately, again, we don't know the exact yet, but we'll talk about that. I would state approximately between 26 and 28, approximately between 26 to 28, okay? And then finally, my spread of my data. A lot of times we look at what's the high and low. So we have a 33 to, and again, about a 14 or 18, depending on what one was an outlier there. So we would say that our spread is between, is 34 minus 18. So it's about a range of 16. We'll again talk about the specifics, and then we put a little context in there to be able to describe what we're talking about in context. Okay, so the logistics of this is we're going to talk about spread, center, outlier, shape, all of that, and how would I describe this? So when we look at this, we talk about this in terms of symmetry, okay, or skewness. So if I had something that was kind of mound-shaped, something that looked like this, I've already used the word, but this would be approximately normal. So again, look at this would be a dot plot, right? So it's a quantitative measurement, meaning it has specific numbers in it. We label it on the bottom, and we look and see, what does dot plot tell us? Well, it's mound-shaped, so we say that it's approximately normal. So we would say that, and that would be sufficient. So approximately normal. Another way to say approximately normal is that it is roughly symmetric. Again, look at the LY words that we put here, meaning that it doesn't have to be perfect, but it's got mirror images either side. Again, it's not perfect, but you'll see that it is either side there. Another way to describe this too, if it has one mound like this, one mound we call unimodal. These are just good words to have when we describe something. Call that unimodal. The next thing, I've already stated this, what it means to be skewed to the right and skewed to the left. If I were to, again, draw this distribution out, because of the fact that the tail is being pulled on the left, we call that skewed. What was it again? Skewed left, yes. Mason's joining us, yes. And then this one would obviously be skewed to the right side, okay? There's a way to remember it. If you look at where it's being skied down, right? He's skiing down to the left, so it's skewed left. If that helps, that's fine as well. Sometimes people look at this as like a big toe. So if you look at your like big toe right here, right? As I look at this, my big toe on my right foot, I don't know if that makes sense. Like it's like goes down, right? There's your big toes here. That's your right foot, whereas this one would be your left foot. Whatever floats your boat, but just some ways to remember it. Center is probably the easier one because you've done this before. A lot of times we have a halfway point between specific values, and that is called our median. So if I were to take the previous example of the dot plot of the 2004 women's team, and I was to find the median value that was there, I would just basically count off by saying, okay, take one there, take one there. And literally what I'm doing is just finding the middle value. Once I find that middle value, that would be called my my median there. And they already gave it to us. If I did that, it would be at 3. If there are 2 values, you would average those values together. If it didn't come down to one middle value, you would just average the 2 middle ones together. There's also another way you could describe center, and that's with mean, or it's just simply the average of the goals. So if I took all of these goals, added all the values up, divided by the total amount of games that were played, the average per game would be 3.06. So the middle value is the median, but the average value, or what we call mean, is 3.06. Both are sufficient measurements of center. Okay. All right. Next thing is spread. Spread is the another way we could say it's the variability. It's how much does the data vary from each other. So if you have a dot plot that looks like this, right? Let's say we draw it out and compare that to a dot plot that looks like this, the one down below, we'll call B, has more variability than A because A is tighter together. One way we can describe variability is by doing the smallest minus the largest value. We call that range. So if I looked at the range of this, we would have 8 goals in a game. One was 0. So 8 minus 0 is 8. Okay. Also, just a heads up, we're going to learn about IQR and standard deviation a little bit later, but just know that those 2 are also measurements of spread that we can use as well. And then finally, outliers. We look and see, is there any specific point within this distribution, this dot plot, that is away from the rest of the pieces of data? There's actually a formula to this. We'll talk about that a little bit later. But just kind of know that if it's way away from all the rest of the pieces of data, we call that an outlier. And a lot of times we throw that out when calculating things like center and things like standard deviation and that sort of thing. But just know that that is something that we can look at as well. For right now, all I need you to know is that 8 could possibly be an outlier because it's way away from the rest of the data that's more towards numbers 0, 1, 2, 3, 4, and 5. Okay. Cool. All right. So this has been an FRQ question almost on every one of the FRQs that I've seen on almost every AP stats exam. So I would make sure that you know this. The one thing they'll ask is to compare the distributions. So if they ask you to compare, to simply talk about both of them is not comparing. You've got to make sure that you mention context, and you must make sure you mention the comparison between the 2. So like if I were to look at this one, if we were to talk over this, and let me do this. Let me take that out. Perfect. Okay. This one's a good one. So if I were to say, okay, let's talk about the Sox and in comparing, first of all, I would establish it with context. So for this one, we're talking about, let's see here, make sure I fill this up here. Okay, we're talking about the household size for South Africa and the UK. So I would start off by saying, when comparing the household size, again, I'm putting context here. I know it seems redundant, but we have to put it. Household size between South Africa and UK. We can see that, and then we would go into, what do you think we'd go into? We just go into Sox, right? We literally compare Sox because we're comparing both dot plots or both distributions that are there. So let's talk about it real quick. What would we compare? Well, let's talk about the shape first. The shape, what would we say about South Africa? I would say that it is skewed to the right, okay? Whereas UK would be approximately normal, right? So that would be the center. We would say South Africa appears to be skewed to the right, whereas UK would be approximately normal. That'd be shape. Outliers. I would say that the UK has no outliers, whereas South Africa has an approximate outlier at 27.5-ish. something like that. That would be outliers. Center, we would say center would be around, what, 7.5 right here? Whereas the UK would be around 5. I would say they're approximately the same. Okay? Approximately the same. We could actually find the median too by, again, going from each side and finding the exact median, but they will be approximately similar, probably around that 5 to 7 mark. That's there. And then finally, my spread, whereas the spread of the South Africa would have a higher range, right? The range would be higher compared to the range of the UK. Okay, and then we would put that down there and rock and roll. I think we've talked about this already, but unimodal is something where we have one mound, right? Or mound shape. So this is one, whereas bimodal should make sense. When we describe shape, we can state this too. Bimodal would be more something that has two mounds, two hills that are there, okay? It won't be two centers. The center will still be somewhere in here, but has two mounds when describing the data there. Here's what I want you to do at home. If you could, just describe this, practice it real quick. See if you could describe the shape, center, spread, and see if there are any outliers that are there. There's no context here for this, so you can pass on that. Oh, actually, there are siblings. So you could actually include the amount of siblings from maybe a random sample at GAC. But see if you could put that down real quick and go from there. All right. One other thing that we're going to hit on more probably, well, I know in class, is kind of our first sample of what an FRQ would be. This is one example of that, and we'll look more into it. This is one that you could probably get a rep on if you want to. But we're comparing the ratio in 10 schools of the highest proportion of students meeting standards compared with the lowest proportion of students meeting standards. And we kind of compare the dot plots there, very similar to what I just did earlier, but just something to kind of keep in the back of your mind. And here would be the solution. So if you want to go and try it out, you could always go back to it. We'll hit on more of these in class, but just something that you would need to do on the FRQ for the AP Stats exam. Notice too, before I could actually compare it, I must first create a dot plot. This is a comparison dot plot where the top would be the high proportion and the bottom would be the low proportion. But notice, again, make sure you put your label there. Okay? All right, let's go to stem and leaf. We are headed towards being done here, and then we'll rock and roll. Stem and leaf is a little bit easier. Another way of describing quantitative data. This is the second one. So we talked about dot plots. This is stem and leaf. We still describe it with socks. So anytime I draw it, make sure we still describe it with shape, outlier, center, spread. In doing this, we separate each observation into a separate stem. We'll talk about that. And the leaf is the final digit. Okay, we'll write all of them from least to greatest, and then we'll arrange them in increasing order. So take a look at this. This would be an example of data that's here. You'll notice that, let's say I was describing 13. I would put the first digit, which is 1, right here. And then the second one I would put is from, again, from least to greatest. So they kind of went here, but really it needs to go to the next step where the 3 will follow. So that represents 13. So you would put, for every 13, you would put a 3, okay? And then 19, I think there's another 13 here. 13, right? Put another 3. You have a 15, you got to put in order. And then a 19, we put a 9. So that would represent 13, 13, 13, 15, and 19. And once I do that, I create, again, my stem, which is my first digit, and my leaf, which is my second digit. Okay, I described that there. So as I look at this from least to greatest, you could kind of see, and you have to kind of look this way, it's kind of skewed to the right side from the least to the greatest values that are there. The big thing to include here is a key that represents one random number. So 4-9, just showing that that would be representative of whatever your context is. In this case, the amount of pairs of shoes that females have. and you just say it represents a female student who reported having 49 pairs of shoes. That's there. That's a heck of a lot of shoes, 49. But yeah, that's how we would describe it there. Okay. Another way we could do it is if we did males and females. So if I said I had a distribution of data with the males and females, I could do what we call back-to-back stem plot. What that means is that we've got the males on one side. Make sure you label that. Females on the other. Make sure you also have your key. So what does the context of that mean? Along with the fact that you have 4 with the -9 representing 49, that's there, 49 shoes. And what you can do is you can then put all of the males on this side. So you've got the males on this side. You'll see this here. And then the females on the other side. Just be careful because a lot of times you're looking at this backwards. So this would still be, again, it would almost be like flipped because it would be from least to greatest. But you're able to compare those two. Again, you would compare them using SOCS. Because again, we're talking still quantitative data that can be measured, okay, measurable data. All right, we'll keep rolling here. Oh yeah, a couple of things. They do not work well with large data, mainly because it's harder to see, okay? Because again, it's hard to put all of those in. So if I had one, let's say that was 43 million, right? That would be really hard to put in a stem plot, right? So it might be easier to use a different distribution for that, just a heads up. Also, sometimes within these, I have to round. So if I have 42,549, I can't put that in a stem plot. I would have to put 43,000 in the stem plot, which would mean that 4-3 is equivalent to the context of 43,000, equivalent to 43,000, which is not necessarily the same as 42,549. So that could produce a problem too. Just a couple of things in terms of stem plot, okay? It's not perfect by any stretch of the imagination. All right, histograms are different than bar graphs. So one thing to remember is bar graphs are categorical from the first video, and histograms are quantitative, okay? So that's the big difference there to remember. When you talk about a histogram, we divide each of the ranges of data into classes of equal width, very similar to how we did on the dot plot. We find the count or percent, depending on whether we're talking about frequency. Again, you remember in video 1.1, or relative frequency, which was related to our percent that's there. And then we want to make sure we label and we scale the graphs accordingly. So if I were to take this, first off, we would represent the fact that each of these states would be a variable compared to their percentage, right? This would be a relative frequency graph, okay? A relative frequency that we'd be using here, all right? Now, once we know it's relative frequency, we can go in and we can then identify how many are within each of the categories. So how many states were between 0 and 5? So instead of having Alabama, and like we did with a bar graph, right? So this would be a bar graph, or you have on the left side, right? You have over here, this would be the percent, and then you would say 2, 4, 6, all the way to, 100 or 20 or whatever. And then instead of putting like Alabama and stating that it goes up to 2.8, right? And then going like that, and then going to the next state, that would take a long time. So this would be a categorical graph. What we're going to do instead is we're going to create a histogram, which is now quantitative, by saying how many states are between 0 and 5% over here. So when we talk about the range of, what was the context again? We're talking about the residents who were born outside of the U.S. We're saying how many residents have a percent between 0 and 5. So we would simply just count them. So we have 1 state, 2 states, and we would go all the way through. Once we do that, we would then count those out. So we would have a frequency table of saying, okay, how many are between 0 and 5? We have 20. How many are between 5 10, 13, and so on and so forth. And to find the frequency within each of these categories, we simply take 20 divided by our total of 50 to get 40%. Same thing, 26%, and then so on and so forth. So then once we set this up, what we can do is then we can create a histogram, because now we're not going to have a categorical, we're going to have quantitative. So what we're going to have is between 0 and we'll go 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, 25 to 30. We want to make sure we label the bottom. So the bottom would be representative of percent of U.S. born, of non-U.S. born citizens, percent of non-U.S. born citizens. And this is the frequency of the amount of states that fell in each category, amount of states in each category, okay? So we could go 1, 2, or you could count by like 2, 4, 6, right? Once I do that, then what we have here is we can just simply plug it in, just like I see here, between 0 and 5, we have a count of 20, right? If you did percents, you could do percents on this, or you could do the number of states. If number of states is what we use, that's frequency. And if it's percent, we call that relative frequency. So from 0 to 5, we go up to 20, right? From 5 to 10, we have 13. So we'll come here. Boom. And again, notice in a bar graph, you have spaces in between. Histograms, you have no spaces. Histograms, again, is quantitative. You have no space between each of them. Okay. 10 to 15, we have 9. So we'll put it here. And you'll see that you just kind of keep going and going and going until we get towards the end. As we get towards the end, we'll notice that over here on this left side, this is the number of states. This is the percent. So this is our frequency. Again, I'm redundant. I'm sorry. But this right here, these terminologies are very important. And then we have relative frequency because of the fact that we have percents. That's the difference. Both of these are skewed to the right. Very good. I heard you at home. Cool. Heard you at home. This would be skewed to the right. Sweet. Oh, man, this is a long graph. Again, notice right over here, gaps in between. This would be a bar graph. There are categories. No gaps. That's a histogram, and that's quantitative. The difference here, okay? So we don't want to make sure we don't confuse those. I want to make sure don't use counts or percents in a relative as data. Not sure what I meant by that, but what we'll do is I think what I'm saying is just make sure you label it. So as over here on this side, if I'm trying to label like what I'm finding and like what this means, make sure like if I'm talking about relative frequency, label that accordingly. Gotcha. Just because a graph looks nice, it's not necessarily a meaningful display of data. Sometimes there might be some things that the way that it's set up throws off or gives a picture that's really not true. So it's important to make sure that you're trying to that it's accurate. That when you label it, that it's accurate. And if it's categorical, you follow a bar graph. And if it's quantitative, you do a histogram. Hey, I hope that was helpful for you. Hopefully we dominated that. I know that was a longer one. But this right here was section 1.2 within our AP stats unit there. And again, inference, bottoms up. I don't think I can say that on a podcast, but probably not. But hey, that's okay. We're live anyway. Have a great day. See y'all. Bye.